Hey there, in this video we're going to talk about dividing polynomials. We're going to look at two different ways to divide polynomials, and one of them you can only use if the divisor or the denominator looks a certain way. So we're going to start with long division. This works for any two polynomials that you're trying to divide. And the first thing we want to be able to do is set up the long division problem correctly. So normally you'll see these written as a fraction. The numerator is the dividend and the divisor is the denominator. Sometimes you'll see them, if you see it with the division symbol with the line and two dots, the first number is the dividend, the second number is the divisor always, or polynomial. And so in the long division, the dividend goes inside the long division symbol and the divisor goes out in front of the long division symbol. So the best way to learn this is to kind of start by refreshing our memory on how to do long division with numbers before we move to polynomials. So the processes are pretty similar. We just have to make some adjustments to the way we think about it when there are variables in there. So let's do an example where we take 296 and divide it by 7. So first thing, we've got to set this up correctly. So the 296 goes inside the long division symbol and the 7 goes out front as the divisor. Okay, so when I'm trying to do long division, I ask myself, well, 7 times what will get me really close to the number inside? And usually we'll try and break it up. Maybe I won't look at the entire number, 296. I would start with just the 2 and say, okay, 7 times what will give me 2? Now, nothing will do that because the 2 is too small. So then I add a digit. So 7 times what will get me close to 29? And well, the answer there is 4. If I do 4 times 7, that's 28. It's as close to 29 as I can get with multiples of 7. And so the 4 goes up above the long division symbol as part of my answer, which we call the answer of a division problem, the quotient. And so the 4 goes up top there. Usually we try and align it with the end of the number that we divided it into, so it would go over the 9. And then that 28 gets subtracted down below. So I have 29 minus 28, which is 1. And then I bring down the digit 6 to get 16 down below. So you subtract the numbers and then drop the next digit down next to it. And then I repeat the process. So 7 times what will get me close to 16? Well, this time it's 2, because 2 times 7 is 14. And so the 2 goes up top next to the 4 in the quotient, and I subtract 14 from 16 down below. And that gives me a 2, and there's no numbers left to drop down. So this is my remainder. Now, you might be thinking of, well, what if I add a 0 to the end? That's if you want a decimal answer. Since we're trying to apply this to polynomials, we're going to go always with the fraction version of this because we can't deal with decimals with polynomials. So the 2 becomes the numerator of a fraction, and it's always over the divisor, which is 7. So my answer becomes 42 and 2/7. That's what I get from this. And so we're going to replicate this process, only we're going to add in variables. So let's look at this example here. 4m squared minus 10m plus 6 divided by 4m plus 2. So I create my long division problem. That numerator goes inside. The 4m plus 2 goes on the outside. Okay, so I'm going to start by asking a very similar question to the last one. Only here, I'm going to focus on the first term of each polynomial. So I ask myself, 4m times what will give me the 4m squared in my long division symbol? And so while thinking about that, 4m times m will give me 4m squared. So that m goes up top as my part of my quotient. And then just like with the numerical long division, I'm going to take that m and I'm going to multiply it by the divisor, 4m plus 2. And I have to distribute that m to all terms in the divisor. So that becomes 4m squared plus 2m. And I'm subtracting that whole thing from the divisor. So 4m squared minus 4m squared is 0 there. So those terms are gone. There's no m squareds. And then negative 10m minus 2m gives me a negative 12m. And then I drop down the next term. And really, you're going to, with this, we usually just drop down all of the terms. So here was just the one, but just drop down the rest of the terms from the polynomial. And then we repeat the process. So 4m times what will give me negative 12m? And well, that's times negative 3. 4m times negative 3 gives me negative 12m. And so the negative 3 goes up as part of my quotient. And again, I take the negative 3 and multiply it by the divisor. So negative 3 times 4m plus 2 is going to give me a negative 12m minus 6. And I'm subtracting that. So I got a lot of double negatives going on here, but it's really important to get those negatives correct. So I have 12m minus negative 12m, which becomes 12m, negative 12m plus 12m. So those are gone. And those first terms should always cancel out when you do this because of how we chose the values. And then 6 minus negative 6 becomes 6 plus 6, or 12. Now, if I try and repeat this again, well, I can't take 4m times a value and get 12 because I already have more variables than what's down below. So the 12 is the remainder of the problem. And I do with it the same we did with the numerical division. I'm going to put it over the divisor, 4m plus 2, and add that to my answer. So my final answer is m minus 3 plus 12 over 4m plus 2. Now it's worth noting that you could actually reduce that fraction a bit because everything is even, so I could reduce everything by 2. Okay, but we've got the divisor at least, even if it's not in its most simplest form here. And you could even note that at the very beginning of the problem, I could have factored a 2 out of every term and simplified it a little bit there to start. Okay, synthetic division is the other way that we divide. Now, this is an example that we just did where synthetic division could not have been used without making some algebraic tweaks because the divisor has that 4 there. If it had just been your variable plus or minus a number, though, then we could have used synthetic division. So synthetic division is a shortcut for polynomial division. Okay, so it can streamline the process. And this can only be done, though, when it's just x minus k, where k is some constant. If you have like an x squared or, more terms than just 2 or constant multiplying by x, then it either doesn't work or you have to make some kind of adjustment. It's a more advanced problem. So synthetic division is kind of a weird one. It's a tough one to describe. So we're going to work through a problem so you can kind of see how this works. It feels a little funny, but just like shortcuts tend to. But this can be a really streamlined way of finding the answer to a division problem without having to go through long division. Okay, so this example, I have x cubed minus 2x squared minus 8x minus 35. And it's all being divided by x minus 5. So I have that nice simple divisor of x minus a constant. So I can do synthetic division here. And we're going to start by focusing on that 5 in the divisor. I'm going to put it in a box. Okay, you always take the opposite of the sign here. So it was subtracting 5. So I put a positive 5 here. If it had been x plus 5, I would have put a negative 5 in the box. Okay, so that goes in the box. And now I'm going to look at the numerator, my dividend, and I'm going to pull out all of the coefficients from all the terms. And you'll notice that I have it's x cubed and then x squared and then x to the first and then a constant. If you have any values or powers of x that are skipped, then you need a 0 for the coefficient for that one. So if there had been no x squared term, for instance, and it went from x cubed to x to the first, then I'd need a 0 as a placeholder so that things line up just like we need things to line up in long division. Okay, so here I don't have that issue, though. I can get numbers for all of them. And so I have 1, negative 2, negative 8, and negative 35 as the coefficients of the numerator. Next, I'm going to leave a little space, and then I'm going to draw a bar underneath all of my coefficients. And I'm ready to start long division, or synthetic division. I've got it all set up. So the first thing you do is you take that leading coefficient, here it's the 1, and you drop it down below the line. Now, the values you get below the line are going to be the coefficients of the answer. Okay, so this is what I'm finding with all this. And so the next step is to take that number that's below the line, multiply by the number in the box, and put it underneath the next coefficient. So 1 times 5 is 5, and so I put that under the next coefficient of negative 2 above my line. And now I'm going to add the numbers in that column. So negative 2 plus 5 gives me a 3. So that'll go down below the line as another coefficient of my answer. And then I repeat that process. So 3 times 5 gives me 15. And I'm going to add that to the next coefficient in line. So -8 plus 15 gives me a 7. And then 7 times 5 gives me a 35. So that goes under the last coefficient. And -35 plus 35 gives me 0. So all I did was arithmetic here. Didn't have to do any tricky stuff. And I now am just one step away from my answer. Okay. The last number that we get in the line of coefficients is the remainder. And so this one did not have a remainder. I got 0. So I'm not going to have a fraction at the end of this answer like I did on the last problem. I just am going to have a nice polynomial. And this is usually a desirable thing that we want that we'll see in later sections. The other 3 numbers, those are the coefficients of the terms. And what I'm going to do to figure out what the power should be is I go back to my original problem. I had a leading term of x cubed. This was a 3rd degree polynomial. The answer will be 1 degree less than this always. So if I started out with an x cubed, my final answer will start with an x squared, just reducing it by 1. And then I just attach the coefficients to it. So the 1 goes with x squared, the 3 goes with x, and the 7 is the constant. So my answer is x squared plus 3x plus 7. And that is how you do synthetic division. Takes a little practice to get used to, so there's some examples below this video for you to try out.